Thank you, Jennifer. Yeah, I'm a bit out of practice because I retired from teaching, so I'm not in the classroom teaching. But I do, of course, still give seminar talks and conference talks. So I'm very excited about this project and being having a fantastic time already here. And this is the appropriate title, I think. Slight change. Okay, so let's see, does it matter when I do this? Yeah. So the goal of the project is, we're saying, expand the family of well-understood linear orderings. And this is that we're thinking of countable orderings. And really we're looking at things of a pretty low Hausdorff rank. So we'll see some that are well understood. In particular, so linear orderings with adjacency, successor, predecessor. So the predicates, which are not immediately, they're not delta 1 definable, right? These are quantifiers. And connections, the computability part aspect is the connections with effective categoricity, which is, say, given two structures that are isomorphic, can you calculate the isomorphism? Can you compute the algorithm to do that isomorphism in some way? And it has a syntactic approach that I like very much. So we will characterize the orders. We'll define these sp-homogeneous orderings. We'll characterize them, and we'll look at the complexity of these notions. Okay, so I've got, I think, yeah, so the main results, I guess, of the paper, I should say it's like a 40-page paper, so it's pretty, I'm not doing everything, but okay. So we'll define and characterize the orderings. We will show that the set of sp-homogeneous orderings is pi05 complete, and actually there's a, beyond that, we have a sigma 06 completion result also, which shows that our characterization is appropriate. You couldn't have a simpler characterization. And then we'll look at the notion of the computability of the isomorphism. So this is, okay, so let's look now. So just, I want to start as slowly as possible. So what do we mean by a homogeneous structure? That any isomorphism between finally generated substructures may be extended to an automorphism of the full structure, okay? And there's a notion of weakly homogeneous. I'm not sure I invented it, but we had a paper where we discussed this. There's a finite set of parameters such that any isomorphism preserving those parameters can be extended to an automorphism. And B is equivalent to saying that if you add the parameters to the language, then it's homogeneous. Okay, so the fundamental homogeneous ordering is the standard ordering of the rationals, eta. We call it eta as an ordering, order type maybe, and Q, maybe, we give it another name. I'm going to generally refer to the orderings, say that orderings are equal, and when I might just mean that they're congruent with each other, that they're isomorphic to each other, to avoid too much confusion. Yeah, so let's think about why is this homogeneous, okay? And so, what's the idea? You look at the rationals and you pick some finite set of parameters and another finite set. And of course, that's isomorphic locally, right? If I have n things and then different things and they're all in the right order, how do I extend that? Well, in fact, you can extend it to a piecewise linear automorphism. Okay, I give an example. So, if you want to doodle and just think about it, yeah, you're just connecting the points, right? You learned that in school, right? Given a pair of points, you can calculate the straight line that connects them together. And if you just do that from A1, B1 to A2, B2, and so on, you get a piecewise linear automorphism. Then you just extend it, out to infinity. So that's straightforward. The other direction might not be so well known, and it gives a little indication of some techniques that we use. This may be as hard of a thing. Okay. So we talk about a successor, right? Two elements. B is the successor of A if A is below B, but there's nothing between them. And that's a successor. So suppose that so if you're not the dense linear ordering, then you have infinitely many successivities, okay? So you just take a pair, you take a successor pair, A and B, and then take a third, there must be a third element because of course there's infinitely many. Yeah. So with Hausdorff generality, it's on the other side. So you would have A less than B, and you also have A less than C. So locally, these two guys are isomorphic. We're hoping there could be an automorphism. But of course, there can't be an automorphism. And why not? Because B, let's see, right. Between A and C, there's somebody there. There's B is there. But between A and B, there's nothing. So you can't extend it to an automorphism. Now we use this technique in more complicated fashions along the way where we're assuming that a structure is what we're going to call sp-homogeneous. And then how do we know what it looks like? Okay. So then we're having the weakly notion. So the weakly homogeneous, now I discussed with parameters. So for example, so you can show it. Weakly homogeneous corresponds to having only finitely many successors. Those would be the parameters. And that means you have a picture of what it looks like, right? It's a finite sum of the dense orders and finite orders. So you could have like 2 plus eta plus 3 plus eta plus 5, or but a finite sum like that. That's exactly what the weakly homogeneous ones look like. Now it's really interesting, and this also comes up a lot during the paper. The fact that stuff like eta plus 1 plus eta, that's just eta. Okay. And eta plus eta is also just eta. Okay. It's more natural. With the one in the middle, you can just think about the interval from 0 to a half, and then a half is there, and then the interval from a half to 1. It's clearly. But it's also true that eta plus eta is really just eta. Each part is dense, and if you take an element from the first eta and one from the second eta, well, they have the first eta has plenty of things to his right, so it's in between. So little tricks like that are a lot of fun. Okay, so the connection with this computability, and I'll try to glide past these type of things, but it turns out, so we have being relatively computably categorical says that given any structures that are isomorphic, there's an isomorphism that can be computed from the atomic diagrams. And without the relatively, it just says if I have computable structures, you can actually compute the isomorphism. And then we generalize. I think for our purposes, we're just going to go up maybe as far as 4, I guess. Delta 4 is as high as we're going to go. But then so delta n categorical would mean there's an isomorphism which is delta n computable in the atomic diagrams. So it's computable when the n's jump. And that basically means that you could ask sigma 3 questions, for example. You could ask sigma 3 and pi 3 questions about the structure before you decide, in order to compute the mapping. Okay, so we'll see. Okay, let's see. Now, a really nice way to think about these the categorical structures is sort of the Scott families. So, hopefully you've seen this. So, a Scott family for a structure, it's a set of formulas that involve infinitely many formulas, presumably, such that every tuple of elements satisfies one of the formulas, and if 2 tuples satisfy the same formula, then they're automorphic. Okay? And then the important idea here is that being delta n categorical just means that you have sigma n Scott formulas. Now, this has to be, well, we say it's a computable family, but that's not really the question here. I mean, basically, you just think, can I think of a sigma n formula? What kind of formula would characterize an element? And it's bound to be effective if you can do it. Okay, yeah, for example, let's see here. What are the Scott family formulas going to be? If I have eta plus 2 plus eta. Okay, so then the elements of the first eta, all you have to say is that x is less than a. Because any 2 elements less than this, the guy in the middle, will be automorphic. Okay, you have an automorphism of eta because eta is homogeneous. Okay. If you're one of the guys in the middle, then you just say the formula is, let's see, I guess I should say x equals Yeah, okay. It should be x equals A, I guess. And x equals B, I guess. Yeah. Right, so you just say who you are. And for the second one, you just say that x, it's in the second part as long as it's greater than B. And those are just quantifier free. Now, for a general, so for a tuple then, which you have to have these first, but for a tuple, you just give the Scott formula for each individual element, and you just tell what order they're in. That's all you need to do. And you have it, okay. All right, so, yeah, so some abstract results are, so given a countable structure with a finite signature, weakly homogeneous implies delta 2 categorical. If without functions, it's computably categorical. Okay. And here the argument, basically you're building an isomorphism, and if you don't have functions, then you always, if you do finitely much at a time, you can calculate, you can build the isomorphism. With a function, the problem is a finitely generated substructure could be infinite. Okay, like you have an omega and you're ordering omega plus A. Well then, immediately you generate the whole thing. So you're trying to, you can't just do one element at a time. You have to do all the way, the whole omega block at the same time, and that adds a quantifier. Okay, so the nice connection here is that you can characterize being weakly homogeneous in terms of the structure, which just has finite many successors, and also you can characterize that these are exactly the relatively computably categorical structures. So it's a nice connection, connecting the computability, the structure, and the notion of homogeneous. Okay. And so we're going to talk about these predicates and functions. So successor function, predecessor function, adjacency. One is next to the other one. I guess I have the y being the bigger one. And then the successor predicate, the predecessor predicate, I am a successor, I am a predecessor. So if we think about the previous slide then, for the weakly homogeneous guys, it's interesting to note that if I add these relations, adjacency, successor, predecessor, these are just relations, and so you're still going to get a computable isomorphism if this is homogeneous. But we're going to look at the functions, and the problem with the functions is that we have an arbitrary ordering. Sometimes there is no successor. So only some things have successor. So we'll deal with that. Okay. Also, just basic things like this. It's important that the notion of the blocks is very important in linear orderings, right? So you can talk about the interval, the points between two elements, and then this block structure is generated. You say two elements are equivalent if they're finitely far apart. So they're in the same block, and I have b of x or bracket ex there. And if you mod out, then you get the quotient structure, the block structure of L. And you can iterate this, we might iterate it a couple of times, but. Okay, so the point of each block is either finite or has type omega star, or zeta. For example, the block structure of omega is just one, it's just one block. And for eta, everything is, blocks are, each individual element is its own block. So the block structure is just eta itself. So I think I wanted to, at this point I realized, oh, I'm at the Hausdorff Institute. Okay, there's Hausdorff rank. So there is some variation on how it's defined by different authors, but we're basically saying you can iterate this block quotient, and the Hausdorff rank, to me, I would like to say, it's the least n such that when you iterate it one more time, nothing changes. Okay, so eta would have rank 0, and I'm sure some papers would say it had rank 1, but 0 and 1 are often, okay. So the only things that have this property, I think, are these the dense structures, and you may have an element, you may have a maximal or a minimal element in your dense ordering, and then if you have a single element, those are the only ones that could be at the end of the day. Yeah, so it's just, if you look at eta plus 2 plus eta plus 3, well, this will have rank 1. The block structure looks like, so the eta stays there, the 2 collapses to 1, the 3 collapses to 1, and then this is eta plus 1. Okay, discussed. So eta plus 1 plus eta is just eta. But you could have something on either end. You could have a 1 on either end for more complicated things. Yeah. Okay. It's a, yeah. I guess if you, right. If you had eta plus eta infinitely, why don't we just, oh, never mind, forget it. There's enough to talk.
Sorry, what about 1 plus eta plus 1?
This starts, got that right? Right. This starts with.
No, sorry, I meant.
Starts here. Doesn't have anything at the beginning. And then, right. So
sorry, I'm asking about
so the one in the middle goes. Well, you're asking up here.
Yeah, that's where I am.
Yeah, I think that those are the only ones that are fixed. I think those are the only ones that would be fixed under the block.
1 plus eta plus 1 also.
I
Yeah,
think.
I'm asking about 1 plus eta plus 1 because.
Oh, right. Both. Yeah, exactly right. Both ends. Yes, the other right. Okay. Thank you. Good to you. Thanks for paying attention. Okay. All right. Okay. So let's see. So let's say. So what about structures that are not homogeneous? I mean, omega is our favorite structure, perhaps. Okay. It's so simple. Why? But of course, it has infinitely many successors. It's not homogeneous, and even if you throw in the relations of successor and predecessor, it's still not homogeneous. Because you could take points that are, like 3 and 5 would be isomorphic. They're both successors, they're both predecessors, and yet there's no automorphism. And then if you add the successor function, which of course is total for omega, this is weakly homogeneous. If you put in a parameter of 0, once you fix 0, then everything it's rigid, like it's rigid anyway. Yeah. Right. And that tells you that omega is relatively delta 2 categorical. Okay, because you have a structure, you will always have an isomorphism which would be computable using the successor relation, the successor function, but that function is required, you can compute that with one quantifier, right? Because we already know if you're asking if you're a successor or not. So, often, when we prove something or say something about omega, we just say, well, of course, then omega star has this, similar result, and that's just because it's the reverse order. Okay. Well, I forgot to do the upper, right? That should be the upper. Okay. So in the reverse order, in a star, these would be reversed. Okay. So, yeah. Okay. So omega. So just as follows, as in the omega star would not be homogeneous with successor and predecessor, but if you had a function, then it would be weakly homogeneous. Okay. So that's omega star. That's the main thing that we're reversing, I would say. So then some complexity results, and these results can be viewed, they have a computability flavor in the sense that if I have a computable ordering, I can do this, but they have a more general thing. If you just looked at the family of all models, of all countable structures with a binary relation, then you would still get this as a uniformly. These would be sigma 2 in the boldface sense. Yeah, so we start to see how complicated things get. Successor being equivalent, it takes 2 quantifiers. The size of the block is really delta 3. That's important. Knowing what the size is. It's a conjunction of sigma 2 and pi 2. Having type omega becomes pi 3. Because you have to say that for every, for every n, there's an nth successor. Okay. Yeah, so successor we define, things are equivalent if there's some finite sequence such that each one is the successor of the previous one, and it starts with the z1 and ends with zn. So these are equivalent. Now this, right, okay. So these definitions are kind of computabilistic, right? Because you're just saying when I say there exists these n things, that's not really a formula in logic, right? But in computability, you can quantify over the n at the same time, right? You're just searching for n elements. Okay. So it would be, I guess in logic, it would be an infinitary formula, right? In some sense. An infinite disjunction over n. Okay, so to create more complicated orderings, we look at this at sums and products, right? So it's understood. So A plus B, you just have a copy of A, followed by a copy of B. All the elements of A are below all the elements of B, and within A and B, they have the ordering that was given by. And I'm sure we all know what the product of structures is. It's this lexicographic order. So you check first, given a pair of elements, one from A and one from B. You check first to see which one is bigger among the B's. And if those are equal, then you look at the A. So for example, this is an important example. So if we just have the n element ordering and then n times eta that's the product ordering, and you can view it as you have a copy of the rationals and you replace every rational with a finite block of size n. So you picture, you look at you're kind of going vertically for a minute there, right? Putting n elements where there was one. Okay, and that's an important structure. It feels like, well, why is it homogeneous? But it's not, because we know it's not, but still. Okay, so Charlie McCoy characterized the relatively delta 2 categorical orderings, and we'll see where that fits in with homogeneous and with our price. It's sort of the ground level of structures. So these structures are the finite sums of orders of these basics, so the basic orders being finite omega star, zeta, and these n times etas. So these are all, it's easy to see that these are delta 2 categorical. Okay, all you just need the successor relation, basically. The successor function to calculate the isomorphism. Okay. Yeah, so at n times eta, as long as you know, given two elements with n times eta, you just want to know where they are in their block. If you have three, if it's just three in every block, the elements will be automorphic. So all the first elements will be automorphic. The middle elements and the last elements will all be automorphic. So you just need to know where you are in that block. And it just takes one quantifier to do that, right? Okay. So the adding them together, there's a trick here that it's interesting. The n times eta guys have to be bracketed on both ends. Of course, not the one on the very end and not the one at the very beginning, but they have to be separate, otherwise it doesn't work. Okay. Yeah. So for example, you can do eta plus omega works because, well, it doesn't look, there's no one there, but omega has an initial element. So that basically works. Okay. And the Scott, yeah, okay. It's support, so yeah, that's the Scott format. So we kind of ran past that earlier, but for elements of omega, you're just saying, if I'm in, where am I in the ordering? So you're just saying there is some sequence of elements, and each one is the successor of the previous one, and it's fixed now, and it's fixed. So this is a fixed formula. Okay, for each individual element, you can tell what the formula is. And then the Scott family would just be the whole collection. So let's see, but omega plus eta is not, because the eta is not separated. Okay, so you can't really tell, given an element, it's hard to tell what's happening with it. Okay, you're looking at a construction. Basically, you see, it seems like if you're gradually building a copy of this, then it might seem that an element, so the border is hazy. It might seem that you've you've got an element with a successor. But as you're enumerating, going through all the elements of your model, well, something might show up that's in between. Then you say, oh no, well, gee, maybe it's in the dense part. And you might think it's in the dense part because for a long time it has nothing next to it, but that something might show up. So you can never be sure. Well, okay, it's just intuition. Okay. So there's a couple things about this. So scattered orderings are generally a simpler class, and we'll just say a couple things about them. So scattered means it has no densely ordered substructure. And so for the scattered orderings, then these are going to be, they don't have the n times zetas, that's all. Okay. So these are just finite sums of finite omega star and zeta. And so those will be the delta 2 categorical ones among the scattered structures. Okay. Now here we go. Okay. So now the thing that we came up with, it's kind of a way I've been looking at problems for several years, looking at areas where you pretty much study relational structures. Okay, I had a lot of work on polynomial time and automatic structures, and there's huge results. Everything's, well, there's quite a lot known about structures that only have relations. But now if we have functions, it's more complicated. So here we're going to say we can extend the function, it's by including the predicates of being successor or not. So the successor, so if you have a successor, then that's the successor. If you don't have one, then you just fix s of x will just be x. So when you calculate that, you know if it has a successor or not. So of course, if I have for example, a computable structure, well, this function won't be computable. It doesn't have to be computable. Okay, because you don't know if it has a successor. And then we say that a structure is sp-homogeneous if with these functions, it's homogeneous. And similarly for weakly or weakly. Okay, so yeah. And so what will these look like then? This will be a very nice family, and I hope you'll agree in many ways. Okay, so in particular, these delta 2 categorical structures are all going to be weakly sp-homogeneous. Okay, and it'll follow from the characterization that we give later. They will all be because of the structure that they have. Okay. Right. So I guess a negative example is always good. So let's see. Right. So we'll notice that omega plus 3 plus omega will not be homogeneous because that type omega is repeated. So if I take a pair from the first copy of omega and an element from the second copy of omega, they could look isomorphic just all by themselves, but the second copy has this finite block below it, and the first one doesn't. So there's no automorphism that can take an element of the first block to the second block. Okay. All right. Yeah, omega plus eta turns out to still be sp-homogeneous, even though it's not one of the special ones. The eta is not bracketed, but that's still going to be true. Okay. And so it follows from previous results, I guess. So if a linear order, if it's weakly sp-homogeneous, then it has to be delta 4 categorical. And that's because, yeah, okay. So it means that there's given 2 copies, there's always an isomorphism that is delta 2 computable in the structures. That is, if I have 0 jump, one jump, I can compute it. But the successor and predecessor functions actually take 2 jumps to compute. Because you have to ask if it's a successor or not. Right, and that's a problem because you're saying, right, is there a God that's my successor? Does it exist? And what does it mean? It means that for anything, that's something in between. So you have 2 quantifiers there. And some of that piles up to be 3 quantifiers. We thought at first, well, surely this is going to be delta 3, but in fact, it's not. Okay, we'll see later. Okay, so let's in the computable model theory, I guess we've studied linear orderings we understand delta 2. Delta 3 categorical orderings we don't understand completely. Okay, there's a lot of question what they look like. And then the delta 4, the rate between delta 3 and delta 4 is not really well understood. So we like to think, we're advancing the field here. Okay, so some more interesting orderings that will be an important part of the SP orderings. The shuffle sum is a very beautiful structure. So it's kind of like the n times eta, but you're using, over each rational, you can put a different finite block, or perhaps an infinite block. So if you had any set of linear orderings, we could shuffle that, at least David claims, okay, you could shuffle them together, you place each rational Q with a copy of some member of A, and you do it so that for each individual order in A, they're dense, or they're all dense, and it's possible to make this more formal by showing that any two such things would be isomorphic. So it can be characterized by that property. So you're thinking of rational numbers, and you're sort of scattering, you're tossing, at every rational you put in a block. Someplace else you put in a block. And then you realize, okay, between these two blocks, I've got to put every other size block. Okay, so you build it by repeatedly placing these structures, these blocks or linear or arbitrary orderings, all everywhere that it could be. Okay. And this is some more magic somehow, the magic of ordering. So the fact that for any linear ordering at all, you shuffle and any set A with a particular element P. So shuffle sum of A, the product with K, you could view as shuffle of A plus P times K plus shuffle of A, and it's just the same as the shuffle of A. Because whatever you do, this condition up here about that these orderings that these blocks are densely everywhere, well, that only applies in the product. It really only applies to the left-hand side, right? Because locally, that means locally everything looks like the shuffle sum of A. Okay, you might have one like shuffle sum of A times omega. You'd have the shuffle sum plus the shuffle sum plus the shuffle sum, and so any element, its block, lives within its own shuffle. Okay, at its particular point. Okay, so these kind of magical things, we could use them. All right. So the first observation, shuffle sums themselves are sp-homogeneous. Okay, and it's not, it's a little bit like showing that eta was homogeneous, but now we have the function. So the point is that given elements from same blocks, okay, I mean it's in the same, because we have given S and P, within a block we can calculate the whole block, right? We could go back and forth and everything. So we can assume that these are different blocks. If these sets of blocks are isomorphic, so A naught and B naught have the same type of a block, and A1 and B1 have the same type of a block, then you can extend this to an automorphism of the whole structure, because intervals between these blocks are all isomorphic to the shuffle sum, okay? Because they're densely ordered with all the, every type of block occurring everywhere. Yeah, so that's all you. So it's similar to the homogeneity of the rationals, right? Between things, you can just connect them up. So one of these blocks, one of these finite sequences is way over here, and the other one is over here somewhere, but you can just shift it over without any problem. Okay, so shuffle sums. Let's see, okay, so then the shuffle sums have to always be delta 4 categorical by the previous observation. On the other hand, okay, so they don't have to be delta 3 categorical. They don't have to be. It does take the full power of 4. And let's just look at, okay, so you can do it. I did a calculation since I'm just a computability theorist at heart, I guess, but essentially you can just observe the shuffle sum of omega plus 1, I forgot the parentheses, it's not going to have a sigma 3 Scott family. Okay, the omega block is really pi 3. To say that I'm in the omega block, that's a pi 3 fact. And you can make that more formal. So any sigma 3 formula that holds of the guy in the omega block, it's because you have these arbitrarily large finite blocks, it's going to hold of some finite guy in a finite block. Okay. And you can make that more formal, sort of back and forth technique, right? So we can't, so we're distinguishing between the 3 and the 4 level. That's an important thing we're trying to do. So we get a characterization of the sp-homogeneous orders. I should, yeah, it seems daunting at first. So it says there's a pairwise disjoint family of sets of which are going to be like the blocks. So the blocks including omega, omega star, and even zeta as possible blocks, which will be shuffle sums. And then for another element, another collection of block sizes, it could occur only once. Okay, you got a block size that could occur only once. And then weakly homogeneous is just a sum of these. Weakly homogeneous is like going from in the picture for the low level, the delta 2 categories, you had omega, omega star, n times zeta, zeta, and you just said, well, let's add these up. And all you're doing, here you're just adding up gives you the weakly part of it. Okay. Yeah, and I have to give a shout out to Selwyn Ng. Keng Meng Ng. He came to Gainesville, he flew from Singapore, came to Gainesville for this conference last spring, and David was there. He flew, so it's 30 plus hours of travel. Checked into the hotel, I sent a message saying, well, I'll be at the office. So he comes by the office, early the next day. Well, actually, it wasn't, even before, I think when he arrives, when he checks in, he comes over to say hello, Say hello, and I said, well, there's something we can work on, I think. I have this idea about sp-homogeneous, I have this idea, just okay, we can work on it. And then he comes back the next morning, had some coffee, okay, and he starts writing this out on the board. He starts writing it out, it's gonna be this, okay? And he starts writing the proof out. He had somehow, instead of sleeping, or he did it, maybe he could do it in his sleep, I guess. I often prove false theorems in my sleep, I don't. But wow. Yeah, okay, so we'll make it we'll elaborate and make it more concrete, maybe. Yeah, so what sense does this make? So, on the other hand, suppose it has this form, and you had this finally generated isomorphism, why would you know that it could be extended? So, okay, so the first thing is, if there's the block types in A, there's only one block of that type in the whole structure for these guys. And so the function has to be the identity there. Nothing to worry about with those guys. And then for the other ones, you get this interval IV, which is a shuffle sum. And of course, if you have this finite isomorphism, then phi of x has to have the same type, right? So V has some finite, or omega, whatever the block size that it has. The image under this isomorphism has to have the same size. That's because we have S and P, right? We have those functions. So if it's an omega block, we're going to see it's going to finally generate the whole thing. All right, and the same thing for the zeta, right? You have the function, so you generate the whole block. And so this isomorphism has to preserve the block size. So that means you live within the same shuffle sum. But we already indicated the shuffle sum is homogeneous. So you get an automorphism of the shuffle sum of the first guy to the shuffle sum of the second guy, but it's inside. And then you just put these together. You do the local isomorphism within the shuffle sum, if it's in one of those. Otherwise, it's the only one of its size, and it maps to itself. So that's to give, you have to prove something in a talk. Okay. The other direction is more difficult. We'll just say a little bit, okay. So we want to use the homogeneous part of it. Okay, so suppose the block. So we'll look at what does the block structure look like? Okay. And then when you look at the block structure, so the set A that we want, the definition, will be the block types that occur only once in the whole structure. That's got to be the special ones. And then the other ones are that are going to go in the shuffles. Where do they go? So otherwise, suppose it appears more than once. Then we claim it's actually going to be an open interval, which will contain all of the elements at all the blocks of that size. And moreover, if that interval contains blocks of other sizes, they will all be densely distributed within that interval. They're all going to be dense. And this is just using the fact that you have these SP functions and just thinking if I take a couple of elements at a time, okay? Because if you think about it, like why are the guys of size 3, let's say, why would they be dense? Well, we said there's at least 2, so you have 2 of them. Now, if there wasn't a third one, well then these 2 guys, they would be isomorphic. They wouldn't be automorphic, right? Because the first one has another one bigger than itself. And the second one doesn't have another one. So by the homogeneity, there must be another one. It's just like arguing that the rationals are densely ordered. Homogeneous means densely ordered, yeah. So there has to be a third one. Then between them, there has to be one, because otherwise you'd have a pair that didn't have something between, and so on. And it also extends if I have different block size in between, that has to also occur all over the place, just using the homogeneity. So not much more difficult than showing that that homogeneous structure has to be dense. Okay, you use the S&P functions that lets you look at the whole block at once. So you're really looking at the block structure. Well, okay, so you could do it, okay. It took a while to sink in, I would say. Direction. So if you think, what does this mean for this? We only realized this like yesterday. So the scattered orderings, there's no shuffle sums, right? So all you have is these finite sums of finite omega star. So really, it's just the relatively categorical ones that we looked at in the beginning. Okay, for the scatter. So for scatter, it's exactly the case that sp-homogeneous is the same as also 2 categorical. All right. So just to elaborate on what things are and aren't sp-homogeneous. So all these. Right, okay. So as long as if I have different block sizes, I can have infinitely many of them, add them up, okay. And these could be shuffles. You can shuffle 1 and 2, then have 3, shuffle 4 and 5. So the 3 and the 6 and the 9, they each occur exactly once, no problem. And these sets are disjoint, right? The 1, 2, and 4, 5, and 7, they're disjoint, so this will fit the definition. Now what about this is an interesting one. So where you have, I think this is, yeah. Maybe I'm thinking weekly, I think maybe here, but okay. I'm breaking this, okay, maybe I shouldn't obsess with that. Let's look at one that's not, yeah. If you do something like a zeta representation, that's not weekly sp-homogeneous because you're repeating the zetas, right? These aren't shuffles, so they can only occur once. Okay? This is scattered, so it can't be. And this would fail because you have the block size 2 repeated there. Okay. Yeah. Forget about that thing with the 5 in the middle. It meant something to me yesterday. Now you can look at the complexity. Now you can extend the complexity by looking at these. What is it? The complexity of looking like eta, or n times eta, or omega times eta. Okay. Yeah, so you get various, you get pi through some are clearly pi 2. Okay, so it takes a little work too. It's easy to see that, like, for example, that being isomorphic to many times eta, that is pi 4. You can give a definition of it. Okay. You're saying that every element for the omega times, every element belongs to an omega block. Well, it takes like the 3 levels or 3 quantifiers. But then you have to also say that both of these blocks are densely ordered. Okay, when you put it all together, you've got 4 quantifiers. And with a little work, you can get completeness. We're doing like, computability theory, you take known complete sets, like the set of the CE sets, which are infinite or co-infinite. You get a couple of quantifiers, and you fool around with the quantifiers, combining structures. Okay, so you get this. We also have this in the more general setting of models. Let's see. Ooh, okay, no, this is computability theory. Let's forget about it. There's always so much time in the day. Okay, to talk about it. Yeah, okay, but then you can now go back to looking at the family of structures. So being homogeneous is pi 2 complete. Being weakly homogeneous is sigma 3 complete. Well, the homogeneous, that follows because it's just eta. It can only be eta, basically, right? So weakly homogeneous becomes sigma 3 complete. You're just putting in the finite sums and finite blocks in between. Okay, and then complexity of being a shuffle sum takes 4 quantifiers. If you specify that the shuffle sum, if you allow these blocks of type omega, these infinite blocks, then it has 5 quantifiers to say that you look like a shuffle sum. Okay, and you can just, I don't think they do that. I wrote out something later, but okay. And then the complexity of the sp-homogeneous, it's sigma 5, it's pi 5, and then weakly is sigma 6 complete. So it's unusual to find concepts that take that many quantifiers. And you can actually, I tried to write out, you can write out the definition. It basically, to be sp-homogeneous for any element, either there was no other block isomorphic to itself, or there was another block of that same type, and then you just say the density. So then for any pair of elements whatsoever, and a third element C, if all these guys are between 2 blocks of type X, so they're in that shuffle sum component, then there must be another block of size Z between. This says they're densely ordered. And if you count the quantifiers and are careful, you will get 5 quantifiers. And then the existential just says there's these parameters. Okay, so we're getting close to the... Yeah, so there's bold places. So so we may be more familiar with this setting. If you look at the space of structures, right? You can look at linear orders within the space of structures, and we get similar results. That looking like eta is pi 2, and times eta is pi 3, omega times eta is pi 4. Okay, but and the upper bound is similar. It's just you just write the quantity, just write the definition and stare at it. But the other direction, the completeness, is totally different techniques. Okay, you're using back and forth techniques that show the completeness. Okay, and then yeah, similarly in this setting of models, you still get the pi 5 complete and the pi 6 complete using back and forth relations between structures. And David is the expert there. Okay, so I defer to him. You're just saying that one element of one structure is lesser equal, it's 3 above an element of another structure, and so on. And next thing you know, okay. So we have that. Then let's see. All right, so we had the question. So these are all delta 4 categorical. You can always have delta 4 isomorphisms between 2 copies. Sometimes there could be delta 3, okay, because the simpler structures are also sp-homogeneous. So we actually characterize. So you're asking Blaise over here. We figured out which ones would be delta 3 categorical and which ones wouldn't be. So they have to have a certain flavor. And that's this condition. It's like we said for the delta 2 categoricals, right? These n times eta blocks were special. They had to have a beginning element, a final element, in order for it to work. So we have conditions, of that flavor. A copy of zeta times zeta can't have something to its left or right, which is a shuffle. You have conditions like that, which just come up when you're trying to do the categoricity. Okay. And so you show they're categorical by exhibiting the Scott formulas, and if the other direction, you show that you don't have Scott formulas. And you use these back and forth techniques. So are we okay? And then, what? I'm either out of time or I've run out. I know I thought we were close to the end. I don't know we were at the end. But let me just think. What else? I guess that's, well, that must be everything then.
Thank you.